Alright, let's do another sample problem for this chain drive topic. And this sample problem is taken from the textbook by Robert Mott, which is one of our reference texts used in this course, Machine Elements Design a Practical Approach. Okay, so this problem says that design a chain drive for a heavily loaded coal conveyor to be driven by a gasoline engine through a mechanical drive. The input speed will be 900 RPM, and the desired output speed is 230 to 240 RPM. The conveyor requires 15 HP. Okay, so that's originally the problem, but I'll just included this additional data or requirements because in the solution they use this actually. So I think it's also helpful if we just state it here as well. Okay, so for the additional data or requirements, it says that we'll just use a design life of 15,000. So that means that the adjusted value would be same as the design power, because 15,000 divided by 15,000, so that's just equal to 1. And we'll use 4 strands, and also we need to check the angle of wrap, and the initial center distance is 40 pitches. So take note, the center distance is given in terms of pitch. Okay, first step for the solution. Okay, let's just go straight to the design power. So solve for the I think we'll just solve directly the adjusted power. Solve for the adjusted power. P sub A is just equal to the design power times the design life all over the service life, right? And this design power is just simply the required power times the service factor all over M. That's the multiple strand factor times this ratio L sub D over all over L sub S. This is 15,000. This is also 15,000. So this is right here 15,000. Oh, sorry. This must be equal to 1. Okay, so the required is 15 HP. So this one is given in HP, and let's just use HP for now, and let's obtain the value of SF. Alright, so SF is equal to, so we have this internal combustion engine with mechanical drive, and we'll use, okay, it says here heavily loaded coal conveyor, so we'll just use these heavy shock loads. This is 1.7, so SF is equal to 1.7, and this is from table 20. And for the multiple strand factor, we'll use this. Since we are going to use the 4, then this multiple strand factor is 3.3. Okay, M is equal to 3.3. This is table 21. Okay, so right here this is 1.7 divided by 3.3, and this is equal to, I think, 6.36 HP. Okay, so if you convert this in terms of watts, then what we get is 4,745 watts. Okay, so the next step is to determine the suitable RC roller chain size using the power rating table. So we will prepare a table right here. This is RC, and then the second row would be the power, and for the number of teeth. Okay, so we'll start with RC 35. Okay, it says here 4,745, right? And that's the required power, and our speed is 900. So right here, here's our speed. So again, power ratings for standard single strand roller chain, number 35. Okay, so here's our RPM, and we need to select a value of 4,700, and we don't get any value right here because this is the maximum. So therefore we go to RC number 40. Okay, so for RC number 40, we are here 900, and we are going to select 4,745. Okay, 4,745. This is it. So we have 4,907, RC40, and this is 4,907. The number of teeth would be 22. Okay, so what else? Also, for the type of lubrications, we are in type B. Let's just write type B lubrication. Okay, and also for the pitch. Okay, for the pitch, we will use table 1. So we are RC4, here's our chain number RC40, and the pitch would be 12.7. Let's go to 12.7 mm, right? Okay, so the next is solve for the other sprocket, so we will use this relation N1T1 is equal to N2T2, and T2 is just equal to 900 times the number of teeth divided by 235. So again, we'll just use this average value of 230 to 240. So the average value is 235. Okay, so with this, what we get is a value of 84.2, and therefore we need to run this to the whole number. So we'll just use 84 instead of using 85. We'll just use 84 teeth. Okay, and okay, we can also do the checking, but I guess we are still in the range. So the next one is to solve for that's right here, solve for the chain length. Okay, so for the chain length, L sub B is equal to 2 times the center distance in pitch plus T sub 1 minus T sub 2 squared all over 4 pi squared times C sub B. Okay, so the center distance is already given in terms of pitch, so we'll just substitute that directly. What we get is 22, okay, plus 84, right, divided by 2 plus 22 minus 84 squared divided by 4 pi squared times 40. Okay, and what we get here is 135.43 pitches, and again we need a whole number for the number of pitch, so 135. We use 135 pitches. Okay, and if we want a length, a unit of length, so this is 135 pitches times 12.7 mm per pitch, right? This is equal to 1,714.5 mm. So that's our length. Okay, so here also it says check the angle of wrap. So recall that in our lecture that the angle of wrap for the smaller sprocket should be greater than 120 degrees. So checking the angle of wrap for the smaller sprocket. Okay, so the equation is this one: theta times s is just equal to 180 degrees minus 2 times the inverse sine of this value. This is, I guess, d sub 1. Right, d sub 1 minus d sub 2 all over 2 times the center distance. Okay, but to solve for this d sub 1, d should be equal to p all over sine 180 all over d. So here's our working equation for the d. So we need to solve first for d sub 1 and then substitute it here. And this one is the center distance, and I guess this is center distance in terms of the unit length. So let's solve first for the d, for the pitch diameter. So d is equal to, this is pitch, is equal to 12.7, right, divided by sine all over 180, okay, divided by the teeth 1, which is, I think this is 22. Okay, so this is 22, and what we get here is 89.2, and for the pitch diameter of the second sprocket, this is 12.7 divided by sine times 180 all over, this is 84, right, 84 teeth, and this is just 339.6. Okay, I think this is in mm. Okay, so therefore theta sub s is equal to 180 degrees minus 2 times the arc sine of 339.6 minus 89.2 all over, okay, so this is 40 pitch, right, 40 pitch times 12.7 mm per pitch, this is pitch. Okay, because this one is should be in unit of length rather than in pitch. So if you substitute all this, what you get is 120.9. So 120.9 degrees. Hey, this is just 0.9 greater than the allowable 120 degrees, and let's just say this is okay. Okay, for now. Or if you want, you can just check for another chain number. Okay, what else? Okay, I guess we can now provide a summary. Next for this, let's just write here 6. So for the summary, for the chain, we have RC40, and the length is equal to 135 pitches, or equal to 1714.5 mm. And also the center distance, this is 40 pitches. Again, we can actually do a back calculation for the center distance. We can also do that, but I think it can, I mean, practically it can be solved by the by providing a take up. Okay, and for the sprocket, we have a 22 teeth, and we also have 84 teeth sprocket, right? What else? And also we need to specify the strand. I think we'll just write that in terms of their notation. I think that's RC 4D, let's say type A, and for the number of teeth here 22, and then another one is 4DA for the type A, or if you want type B or type C, anyway, whatever. Okay, so here's our specification, and the lubrication is type B. Okay, so that's it. Okay, so what's new in this problem is that we were able to solve for the angle of wrap, and also for the pitch diameter. Okay, so I think that's all, and in our next lecture we will discuss the spur gear drives, and I think that and I think there's nothing much left to say. Okay, so see you in the next video.